video is about superconductors, especially ceramic high-temperature superconductors, and their amazing properties which allow for the levitation you see here. These superconductors have the potential to create dramatic advances in many engineering systems, from electric motors to cars to wires.
In order to understand superconductivity, we must first understand what conductivity is. Conductivity is the flow of electrons through any material. Every electron is independent from each other, but they all flow in the general current flow from high to low voltage. Conductivity is directly related to resistance. As you can see in this image, resistance is anything that slows electrons down in a material, thereby decreasing current flow. Resistance is largely caused by atomic vibrations. At a lower temperature, there are fewer atomic vibrations, therefore reducing resistance. This is illustrated in the table shown. Every material has a higher conductivity with a lower temperature. Impurities also cause resistance because there is a higher rate of electron collision.
Superconductivity was originally just thought of as the ideal perfect conductivity in which no resistance is exhibited. And while superconductors do exhibit the property of having no resistance, differences can be seen between a superconductor and the predicted perfect conductivity by how resistance changes with temperature in a superconducting material. As you can see in this image, rather than resistance going to zero as would be linearly predicted, at a certain superconducting temperature, resistance suddenly drops off to zero from a number well above that. The differences between superconductivity and perfect conductivity can also be seen in how a superconductor influences a magnetic field around it. There are two types of superconductors, type 1 and type 2. As you can see in this image of a type 1 superconductor, the magnetic field is unaffected by the superconductor until it reaches the superconducting temperature, at which point all magnetic field lines are repelled by the material. In this image of a type 2 superconductor, you can see that it actually does allow through, even at superconducting temperatures, some of the magnetic field. However, it only allows it through at very specific vortice points. This is important in allowing for a superconducting material to remain fixed in the air over a magnetic track. As opposed to the original theory of perfect conductivity, superconductivity can actually only be explained using quantum mechanics. In a metal where electron C bonding is present, superconductivity has been explained as all the electrons in a material coming together as one entity and moving through the material, all in the same phase, held together by lattice vibrations. Unfortunately, this theory can only be applied to low-temperature metal superconductors, which were first discovered. In high-temperature ceramic superconductors, which we are most interested in, this theory cannot be applied since electron C bonding is not present. Instead, superconductivity in these materials is not yet fully understood. These high-temperature superconductors operate at temperatures of about negative 170 degrees Celsius, just above the temperature of liquid nitrogen.
It is ceramics that can become superconductive at high temperature. Although we don't understand how superconductivity works, scientists have discovered ways to raise the temperature at which materials can become superconductive. There are a few trends in the structure of the superconductors that scientists have observed. As can be seen in this image, high-temperature superconductors typically have a distorted perovskite crystal structure with layers of copper dioxide planes are contained within this structure. Having more of those planes is the key to increasing superconductivity critical temperature. Much like how grain boundaries deter conductivity in regular materials, grain boundaries in these copper dioxide planes also deter superconductivity. Therefore, most high-temperature superconductors have large grains and therefore fewer grain boundaries.
In order to meet these specific structure goals, extensive processing is often required. As seen here, all high-temperature superconductors contain copper dioxide, but there are many other element combinations. There are many new combinations of elements with copper dioxide still being tested to see if they can increase the density of copper dioxide planes in the crystal structure. In addition to merely combining these elements, an initial heat treatment is applied to help achieve the desired crystal structure. Another processing method used to attain the desired structure in high-temperature superconductors is annealing. Annealing is the process of heating a metal without melting it. This will cause new grains to grow and replace the original grains. While the video shows a metal, the process is identical for ceramics. In addition to regular annealing, oxygen gas is usually run through the material during annealing to aid in the formation of the copper dioxide planes. This process of annealing, in addition of oxygen, is a process often repeated several times in an attempt to raise the initial superconducting temperature.
And ceramic superconductors are too brittle to be drawn into wires via normal wire drawing processes,
Processing methods such as chemical vapor deposition have been developed, in which a chemical reaction is used to deposit a thin layer of the ceramic on top of another material.
As we have made clear so far, the ultimate result of this processing is to create a material that exhibits superconductivity with zero electrical resistance at increasingly high temperature. The levitation made possible in this experiment by the way magnets fields interact with the superconductors make for a cool video, but ultimately it does not matter if it cannot be applied to real-world problems. Luckily, high-temperature superconductivity have the potential to radically alter several major engineering fields.
If room temperature superconductivity were achieved, mass transport could also be revolutionized. A levitating car could be achieved without huge energy input through superconductors placed on the road, similarly to superconducting trains that already exist. In cars today, 49% of power to the wheels is lost to air resistance, and 28% is lost to rolling resistance. A levitating car could vastly reduce these losses, because as you can see in this image of a superconducting car concept, no wheels would be required, entirely eliminating rolling resistance. Also, the absence of the chassis and wheels allows for an aerodynamic underbody and a reduced amount of air travel.
One area where high-temperature superconductivity is already applied can be found in mass transit. Japan is already testing superconducting maglev trains. In fact, these very trains have recently set train speed records. These trains have been recorded traveling up to 361 miles per hour. Such speed encourages train use, and though current superconductors do still require liquid nitrogen for cooling, they use much less energy than traditional non-superconducting maglev systems. If room temperature superconductivity is achieved, these trains would have even more advantages over traditional systems thanks to reduced energy use and higher speeds.
Superconductivity also has the potential to greatly improve wires. Current power transmission techniques result in 6.5% of electricity losses in the US. These losses are almost entirely due to resistance within the copper or aluminum wires, resistance which would be completely eliminated if superconducting wires were used instead. While such wires have already been developed, as can be seen in this image, they currently have the drawbacks of being complex because they require liquid nitrogen for cooling. Room temperature superconductors would remedy this problem.
One other piece of technology which could be vastly improved by room temperature superconductors is electric motors. Traditional electric motors, such as the one shown, are often very large due to the size of the electromagnets they use and the amount of insulation they require. Room temperature superconductors would allow for motors to be at least 90% lighter.
Once we discover the right processing techniques to achieve room temperature superconductors, huge advancements in fields ranging from electrical engineering to transportation will be made. These advancements could make travel more efficient, cut down pollutions from vehicles, and make our everyday lives easier. If achieved, room temperature superconductors would be the invention of the century.